Hello, today I'll be presenting to you the derivation of Fresnel equations. So what are exactly Fresnel equations? So we described how an EM wave is split into reflected and transmitted or refracted components when it encounters an interface with different refractive indices, which we call N1 and N2 in this case, or we can also say different permittivities or different impedances. This is how we define our problem. This is our coordinate axis. Where the materials, first the material refractive index N1 will be on the bottom and N2 on the top, and our interface, as we're gonna see, will be the XZ plane. Okay, the YX plane is what we call the plane of incidence, and it's where we define whether we are working with a polarized wave or an S polarized wave. Okay, and the XZ plane is where it is the interface of the two mediums, and it's where we're going to define the boundary conditions for our problem. So we're going to assume that we have a wave, an electromagnetic wave, okay, that is coming into that is incident into our interface here, where and it's making an angle theta I, okay, and intuitively what will happen is that this incident wave, when it hits the interface, it will either reflect with an angle theta r, or uh, be transmitted into the second medium here, okay? And if we either say transmitted or refracted, okay? So uh, the this is called the refracted wave. So first, let's start with the perpendicular polarization, or also the S polarization, or where the electric field is perpendicular to the plane of incidence. So this is why we call it S polarization. Um, we can also call it transverse electric polarization because the electric field is transverse to the plane of incidence. So let's take the problem that we defined earlier. So the arrows here the arrows, they represent the direction of our EM wave, which is also called the K vector. Okay, so this is the K vector. We have the incident K vector, okay, which is denoted by here Ki. And the way that we define, because we have said that it's a transverse electric wave or an S polarization, the electric field will be polarized towards the positive z-axis. So we can see that when it's polarized towards the positive z-axis, it will be indeed transverse to the plane of incidence, which we said is the xy plane. And we also defined the magnetic field, okay, Hi, which will be in the plane of incidence, the yx plane, okay. And it's important because the three need to be perpendicular to each one of another. And we can also do the same thing for the reflected wave, or we have the reflected K vector and the following electric field and magnetic field, and the refracted K vector, or the transmitted K vector, where we have the following electric and magnetic fields. Now, let's assume, in order to simplify the math, that the EM waves that we are working with are plane waves in an homogeneous and isotropic medium. So that means that the incident electric field will take this form. You can see that it's a plane wave where indeed we have our electric field that is polarized towards the positive z-axis, as we can see here. And because we are talking about the incident electric field, we have in the exponent, we have the incident k vector. There is dot product with the position vector, which in this case is the standard coordinate axis xyz. So in later slides, we're going to define what is this ki. What is the expression of the ki vector? And in the same manner, we can do the same for the reflected electric field and the refracted electric field, where again they are um, plane waves, where they have the same form as the incident electric field. However, in the exponent, we have for the reflected electric field, we have the reflected K vector, and for the refracted electric field, we have the refracted K vector. So we are working with, as we said, the position vector, which is the standard coordinate system. And how do we find the respective K vectors? We can see that they are in the XY plane. So, and each of them make an angle theta. For example, for the incident K vector, it makes an angle theta I. So we can actually express these K vectors in terms of the respective angles. For example, let's take an example of the incident K vector as a function of theta I. It will be as such. So for the incident K vector, it will be equal the K1. K1 is actually the wave number inside of the first medium times this vector here. Okay, where we have for the x position, it will be the sine theta I. And why? Because we can use the rules of trigonometry where we have sinus of this angle here, and we're gonna find that if we rearrange all the terms, it's going to equal theta I, sine theta I. And we can do the same for the cosine of this angle, and we're going to find cos theta I, and it's zero here. It's because there's no dependence along z for the incident k vector. We can do the same thing for the reflected k vector, where we have sinus theta r minus cosine theta r. And why the minus? It's because when we look at the direction of the reflected k vector, we can see that in the y-axis, it goes into the negative. So this is why we have a negative sign here. And again, zero here. And we can do the same thing for the kt vector, the refracted k vector, where it is in the same like it the arrow is um, in the positive xy axis, and this is why it is equals sinus theta t and cosine theta t. And we need to pay close attention to the fact that we can see that for the incident k vector and the reflected k vector, it is k1 times the respective vectors, and this is because we are in the first medium. However, for the refracted k vector, it is k2 times its respective k vector, okay? Respective vector. Um, and these are the expression for the wave numbers, where we can clearly see that for the k1 wave number, it is equal this expression here, so 2 pi over lambda in the medium, so the wavelength inside of the first medium, and for k2 it's the 2 pi over the wavelength inside of the second medium. In this manner, because we found each respective k vectors, we can express the incident electric field as such, where we have now this expression here. Okay, so now it's equal k1 times this vector times x, because we have the standard the position vector, so it's a dot product. And for the y, we can do the same for the y coordinate. And now for the reflected electric field, we can do the same, where we take this k vector times the position vector. And for the refracted electric field, we have this following expression. So now let's focus on the magnetic field and how do we express them. Uh, we do the same thing as the k vectors. We express them in terms of this theta I angle. How do we do so? So what we're gonna do, for example, for the incident magnetic field, we're gonna bring the coordinate system into here. So now we have this new coordinate system here, And so it's the minus yx coordinate system. And now we can see, so the green arrow is the incident magnetic field, and it's going to make the same angle theta I here. So this theta I and theta R here are equal. So these are the rules, basic rules of um, angles. And now we can express the magnetic field in terms of this new theta I, which is the same as this theta I. So we use the rules of Sohcahtoa again, uh, and we can see that now the incident magnetic field is equal to such. So we can see that because it's pointing in the positive x direction, and if it's going to equal cosine of theta I, and it's in the negative, and because it's in negative y direction, it's going to give us minus theta I for this here, times h0, so it's an arbitrary amplitude for magnetic field that we're going to figure out later. And we can do the same thing, and also it's times this exponent here, which is the same exponent as the incident electric field. So we can, and then we can do the same thing for the reflected magnetic field and the refracted magnetic field. For good measures, let's verify whether our calculations are correct, whether the directions of each vector is correct. So because in EM waves, especially like plane waves, it is important to verify that each component, that is the electric, magnetic, and K vectors, are orthogonal to each one to another. Okay, so let's verify. So this is the unit vector for the incident electric field, which is 0, 0, z, because it is polarized along the z axis, as we positive z axis, as we saw earlier, and the unit vector times dot producted with the unit vector of the incident magnetic field, and we can clearly see that it's equal to 0 here. So if we do the dot product, and we can do the same thing for the incident electric field dot produced with the K vector, where we find it's also equal to 0, which proves that it's orthogonal. And we do the same thing for the magnetic field and the K vector, where we can see that if we do dot product of both of them, it's equal to 0. So so far so good. We can do the same thing for, now I just saw an example for the incident fields, but you can do the same thing for the reflected field and refracted field, and you can verify that they are indeed orthogonal and that so far everything is correct. So now let's start defining the boundary conditions of our problem. So we said that the interface is the XZ plane. So it's a 2D interface that we assume that is infinite, okay? And so these are the following boundary conditions for our electric field. First, we need to, the first boundary condition is that the tangential component at the interface of the electric field should be continuous, which means that the electric field at the tangential electric field in the first medium should be equal to the tangential electric field at the second medium at the interface. And also, we have the same thing applying to the displacement field, where its normal component should be continuous along the interface. Um, so we can also actually rewrite the tangential electric field at the first medium as the sum of the incident and reflected electric field. So the tangential components, and because there's only the refracted component at the second medium, it will be only equal to ET. We can do the same for the second medium. And it's continuous in this case for the normal component, is because we are working with dielectrics, and dielectrics, we assume that there are no surface charges. So this is why we assume that they're continuous. So yeah, so it's continuous because there are no surface charges. And we know that the electric field is polarized on the z-axis, okay? And we know that our interface is the xz plane. And so that means the electric field is actually tangential to our xz plane, okay? So, and there are no normal components ey. So actually this expression will be equal to 0 because there are no normal components. So we can only work with the tangential component, and we define it as this, okay? So we only work with this component. So we can derive the tangential component of the electric field at the interface um, as such. So we start with the expression that we defined earlier, and we know that the tangential electric field is the one that is polarized in the z-axis, which is what we derived earlier, and because it is tangential to the xz plane, so we can write the same expression for the um, incident electric field and the reflected electric field and the transmitted electric fields. And if you see how we defined our problem earlier, we can see that the interface is the xz plane, and it's at y equals 0. So it's at y equals 0. And in this case, because y equals 0 in this case, we can set the y's of each electric fields to be equal to 0, and we can simplify it as such. And we also can get rid of the time dependence of the electric fields, where when you factorize them, we can factorize them and cancel them, and we are left with this final expression here that we need to satisfy at the interface. So how do we satisfy this expression? So we need to employ, in order to satisfy this equation, it means that this each term in the exponent should be equal. So that means this term should be equal to this term and should be equal to this term in order to satisfy this expression here. So this is what we call phase matching. Okay, so we can see that this should be all equal. And actually, this is in the next slide, this is where we actually derive Snell's law from, and also the law of reflection. So now, by taking the previous expression, so for phase matching, we can uh, define the following wave numbers as such. So for medium with refractive index n1, and for medium with refractive index n2. And now we can further cancel out the 2 pi over lambda naught for each, and we get the following expression here, where it encompasses the Snell's law and as well as the law of reflection, where here we have the rule of reflection. That means in order to satisfy this expression, that means that the angle of the incident and reflected field should be equal. Okay, and here we have Snell's law here, so which is, yeah, Snell's law. In a similar fashion, the magnetic field needs to obey the Maxwell boundary conditions, where the tangential component of the magnetic field should be continuous at the interface. Here it's continuous specifically because we are working again with dielectric. So because normally in standard boundary conditions, the tangential component of the magnetic field is discontinuous, but because there's no charge density at the interface, then it's continuous. And here, naturally, for the magnetic field, again, it is the normal component is continuous. Again, we define the magnetic field at each medium, where it is the sum of the incident and reflected magnetic fields being equal to the refracted magnetic field. So the interface is the x-plane, as we said earlier, and because the x-plane, that means magnetic field will have like a polarized component. So the magnetic field is polar. We can see that the vector is polarized along the x, y axis, which means that it presents one tangential component hx and one normal component hy. So unlike the electric field, the magnetic field has tangential components and normal components. Like the electric field, we can derive the tangential boundary um, component of the magnetic field. So we said that it's only the x component of the magnetic field that is tangential to the interface. So we can write the magnetic field as such. So now it's we only take the x component because we said that it was polarized along xy. So but here it's only the x component that we take, and it is written in this manner. And because the interface is the x-plane and we the EM wave is at y, the plane is at y equals 0, we can get rid of the y uh, dependence in the exponent, and again factorize the time dependence, and we get this final expression here of the um, condition. However, we see that there's an S0 here, okay, that we can actually, because we are working with EM propagating waves in a medium, we can actually express the magnetic field amplitude as such. So if we derive the curl of the curl of the electric field, we're gonna find that the amplitude term has this form here. So now that we have this expression here, we can actually uh, replace it in the expression, and it's going to be equal this expression as such. So we express now the magnetic fields in terms of the electric field. So now we can see that we have now h0 is equal E0 over c, being the speed of light times the refractive index in medium 1, and the other on the left and on the right hand side we have it equal to n2, and we can see that it is now, we can take this expression here and as well as this one and as this one, when we can set it equal to this following final expression. So now that we've derived the boundary conditions for both the electric field and the magnetic field, and that we have expressed the magnetic field in terms of the electric field, we can then conclude with a system of equations as such. So we have indeed expressed the magnetic field and we can see that now that we express the magnetic field in terms of the electric field, we can have this following system of equations. And we can see now, because we have they're all over the speed of light in the second expression here, we can cancel them out, and also we can bring the the n1 refractive index into the right hand side, and we can get the following expression here. Now that we've said that the law of reflection should be satisfied, that is, theta I should be equal to theta R from the previous phase matching condition, we can now set this equal to cos theta I, and we can factorize theta I as such. So from the law of reflection, we can have this following expression here. And we can finally bring this cos theta I to the right hand side and get this expression here. And this is important to find what will be the reflected electric field and the transmitted electric field for S polarization. So now taking the previous expression, we can, how do we find the transmission coefficient for S polarization? So we need to cancel out the reflected electric field here. And how do we do so? We can simply add them together. So when we add them together, we're going to find the refracted electric field component, and it is going to be into this form. And so the transmission coefficient for the S polarization is actually the ratio of the transmitted electric field over the incident electric field. So now that we have this, we can rearrange all the terms in order to find the transmission coefficient for S polarization, which is annotated by uh, T perpendicular. So it's important to make the clarification is S polarization because it's perpendicular to the plane of incidence. So this is why it's T perpendicular, which is equal to this, the ratio of the transmitted over the reflected electric field, and we get this final expression. Now, in order to find the reflection coefficient for S polarization, we take again the initial expression that we found earlier, but all we did was move all this cosine and diffractive index to the other side such that we can cancel out the transmitted electric field. So now we can do just the difference between the first and the second expression as such, and we can rearrange all the terms to find the reflection coefficient, which is the ratio of the reflected electric field over the incident electric field. And we get this following final expression for the reflection coefficient for S polarization. Now for P polarization, where the electric field is parallel to the plane of incidence, it will look, the scenario would be the following. So now instead of the electric field being normal to the plane of incidence, it will actually be in the plane of incidence. So, and we can use the exact same um, steps as the previous case, which these are the general steps. We just assume that we're working with plane waves, and then we find what are the expressions for the k vector, and then we find the expression for the, now we're gonna find the expression for the electric field that is in the plane of incidence, and we can verify the orthogonality of components, which is an extra step just to make sure that our calculations are correct. We find the E and H field vectors by applying boundary conditions, and then we find which components are tangential or normal to the normal of the interface in order to derive a system of equations. And we can find the reflected and transmitted coefficient for the P polarization. And by deriving, you should be able to find the following expressions for P polarization, which this is the reflection coefficient for P polarization and the refracted component as such. So I hope this video helped you, and thank you very much for your attention.